Hi everyone. So today we're going to finish up our exploration of Chapter 6 by talking about a method for computing limits that we otherwise can't really make progress on. And so we're going to show some examples and applications and the motivation for a method called L'Hopital's rule. When you were in Calculus 1, you would have been introduced to the idea of a limit, which is a way of looking at the behavior of a function as its input approaches a certain value. In some cases, this is very easy to do. So you could ask a question like, what is the limit as x goes to 2 of x squared minus 1 over x squared plus 3x plus 2? And what you would have learned here is that the first thing you try is to plug in the number 2. 2 squared minus 1 over 2 squared plus 6 plus 2, which is 3 over 12. And so this is the limit. That method of computation relied on the fact that the function was continuous at x equals 2. So in here, what we've used is the fact that x squared minus 1 over x squared plus 3x plus 2 is continuous at x is equal to 2. And when we looked at the definition of continuity, one of the things that we learned was to say that f is continuous is to say that f of a is equal to the limit as x goes to a of f of x, which is to say a function is continuous if you're allowed to just plug limits in at that point. What if we try to compute a limit at a place where a function isn't continuous? So we're going to use the same exact function that we used before, but I'm going to change where I'm evaluating the limit. So let's look at the limit as x goes now not to 2, but to negative 1 of the function x squared minus 1 over x squared plus 3x plus 2. Now, if you try to just plug a number into this function, you're going to end up with something kind of weird, because the top turns into minus 1 squared minus 1, which is 0, and the bottom turns into minus 1 squared plus 3 times minus 1 plus 2, which is also 0. So what you would have learned when you saw this for the first time is that if you have rational functions, like this one right here is a rational function. So in the case where you have a rational function, that is to say, a polynomial divided by another polynomial, and you get this 0 over 0 form, that is, you get a 0 on top and a 0 on bottom, that you can factor and cancel. And what you get when you do that is x plus 1, x minus 1 over x plus 2, x plus 1. And you can see that the problem here is in these x plus 1s, because if I take the number negative 1 and I plug it into x plus 1, I get 0. And if I take the negative 1 and I put it into this x plus 1, I get 0. But the same term occurs on the top and bottom of the fraction. So you could just cancel those. And it turns out to be the case that the limits are the same after doing that cancellation. The limit as x goes to negative 1 of x minus 1 over x plus 2, which is minus 1 over minus 1 plus 2, which is negative 2. So what you learned was if you got 0 over 0, you had to do algebra, cancel, and try again. What if you can't do that? What if we're going to get a function where we get the same thing, where we have the top is 0 and the bottom is also 0, but there's no factoring or cancellation to do? Can I still compute a limit of that function as the input approaches a value? So as the example that I want to think about, let's think about the function f of x is equal to the natural log of x over x minus 1. So this function has an asymptote at the point x is equal to 1, clearly, because if you put a 1 in here, you get a 0 on bottom. So x is equal to 1 is not part of the domain of the function. I could still ask if this function has a predictable behavior as the inputs approach the point x is equal to 1. So I could still ask the question, what is the limit as x goes to 1 of the natural log of x over x minus 1? We have the same problem here that we had before. If I plug 1 into the top, I get the natural log of 1 is 0. If I plug 1 into the bottom, I get 1 minus 1, which is also 0. But 0 over 0 isn't a form I can say anything about. And this time, I can't factor natural log in some way that an x minus 1 is going to fall out of it, and there's some kind of algebraic cancellation that happens. A similar question would look at, say, what happens to this function as x goes to infinity. That is, what is the end behavior of the function, or the asymptotic behavior? What is the limit as x goes to infinity of the natural log of x over x minus 1? Well, in that case, the natural log of x goes to infinity as x goes to infinity. And x minus 1 goes to infinity as x goes to infinity. If you put gigantic, huge numbers into x minus 1 and you subtract 1 from a gigantic, huge number, it's still a gigantic, huge number. So this is also going to infinity. So this looks like infinity divided by infinity. Now what? I can't say anything about that either. So these shapes here, where you have functions that look like 0 over 0, or functions that look like infinity over infinity, are called indeterminate forms, because we don't actually know what the limit is. Sometimes with an indeterminate form, we could do what we did on the last slide, which is to say we can factor and cancel. But for a lot of functions, there is no factoring and canceling. So we're going to have to come up with a different tool. The tool that we're going to use is called L'Hopital's rule. So this is written a couple of different ways. You could see it as L'Hopital with an S. You could see it as L'Hopital with a little breve over the top of the O. Either way, it's not La Hospital, it's L'Hopital. And what L'Hopital's rule says is that if you have a function of the form 0 over 0 or infinity over infinity when you take the limit at a point, that instead of working with the ratio of functions, you can work with the ratio of their derivatives. So suppose that f and g are differentiable, and that g prime of x is not equal to 0 on some open interval containing a point A, and, I guess I should say, except maybe at A. That could happen, it's still okay. So the setup here is I have two differentiable functions, and that as I get closer and closer to the point A that I'm going to be interested in as my input, that there's some little interval around A where the denominator is not equal to 0. Then, if f of x goes to 0 and g of x goes to 0 as x goes to A, or alternatively, f of x goes to plus or minus infinity and g of x goes to plus or minus infinity, then the limit as x goes to A of the ratio of f of x to g of x is equal to the limit as x goes to A of f prime of x over g prime of x. And this is not a quotient rule. This is that the limit that I'm taking here on the top, this limit right here, the limit of the ratio of the functions, is equal to the limit of the ratio of the derivatives. So I take the numerator and I take its derivative, I take the denominator and I take its derivative. The first question you should have is, why should that possibly be true? Like, that doesn't make any sense to me. That the value of the two functions, the ratio of the values, is equal to the ratio of the slopes of the tangent lines seems like an absurd statement to make without any sort of backup or verification. So what I want to do is I want to give you an idea of what a proof looks like in a simple case that will hopefully convince you that this is a property that we can think of as a property that makes sense. And so we're going to be looking at a special case here. This is not a proof of the theorem that I've written, but it is going to be a proof in a very powerful special case. Why should we think that that is true? So this is a proof in a special case. What we're going to do is we're going to make the assumption that the functions have not just derivatives, but they have continuous derivatives. So suppose that f and g are continuously differentiable, which is to say that the derivatives are continuous. The reason that we're going to want to do that is because we're going to want to plug limits into the derivative functions. And if they're not continuous, then we can't do that. So we need one more condition which is that the functions approach 0 and not infinity as x goes to a. The argument that for the fact that we can assume that is that if f goes to 0, then 1 over f goes to infinity. So if I can show the argument holds for functions that tend to 0, I automatically am going to get an argument for functions that tend to infinity as well. Let's assume that f of a is equal to g of a and that both of those are equal to 0. Again, remember that if f goes to infinity, that 1 over f goes to 0, and so we're not really losing any generality by making that particular assumption. So how does the argument go? Well, the limit as x goes to a of f prime of x over g prime of x, if I rewrote that using the definition of the derivative, what I would get would be that this is equal to the limit as x goes to a of f of x minus f of a over x minus a, because that's the definition of f prime, divided by g of x minus g of a over x minus a, because that's the definition of g prime. Now, if I invert the denominator and I multiply through, the x minus a's will cancel, and this turns into the limit as x goes to a of f of x minus f of a over g of x minus g of a. But g of a and f of a were both 0 by assumption. We made the assumption that f and g were both 0 here. And so that means that we could write down that this is equal to the limit as x goes to a of f of x minus 0 over g of x minus 0, which is the limit as x goes to a of f of x over g of x. It's not at all obvious that this should be the case. So it's a surprising result, but it's also a very powerful and useful one. So let's look at some of the limits we've already looked at and see if we can apply L'Hopital's rule. The first thing that I want to say is you must verify when you're using L'Hopital's rule that you're working with an indeterminate form. So you must verify that you're looking at a ratio of the form 0 over 0 or infinity over infinity. That has to be written someplace where I can tell that you've checked that condition before you apply L'Hopital's rule, because it's possible to write down an expression that looks like you can apply L'Hopital's rule to it, but you can't. And then you get the answer wrong. Let's look at the limit as x goes to 1 of the natural log of x over x minus 1. So I'm going to verify first that I'm working with an indeterminate form. If I think about what happens as x goes to 1 of the natural log of x just by plugging it in, well, the natural log of 1 is 0. X minus 1 as x goes to 1 also tends to 0. I've got a 0 over 0 form, and that means I'm justified in applying L'Hopital's rule. A lot of times in problems like this, it's typical to write an LH somewhere to indicate that this is what you've used to step from one part of the process to the next part. This is equal to, then, by L'Hopital's rule, the limit as x goes to 1 of the derivative of the natural log of x divided by the derivative of x minus 1. Notice this is not a quotient rule. I am taking the derivative of the numerator and dividing by the derivative of the denominator. So L'Hopital's rule is easier to use than the quotient rule. If you continue, this turns into the limit as x tends to 1 of 1 over x over 1. The derivative of natural log is 1 over x. The derivative of x minus 1 is 1. Algebraically simplifying, we get the limit as x goes to 1 of 1 over x. Well, that function is continuous at x equals 1. I can just plug the number in. So this is equal to 1 over 1, which is 1. And there's really no other way to do this problem other than numerically estimate. But from an analytical standpoint, this is the correct approach, is to use L'Hopital's rule. Let's see what happens at the asymptote as we run out to infinity in x. As before, I need to verify that I'm working with an indeterminate form. So if I look at the top and I look at the bottom, as x goes to infinity, the natural log also tends to infinity, because natural log is a function that looks like this. So natural log does tend to infinity as x goes to infinity. X minus 1 tends to infinity as x goes to infinity. So we're looking at an infinity over infinity indeterminate form, but we can use L'Hopital's rule in that case as well. So we can rewrite this by L'Hopital's rule as the limit as x goes to infinity of the derivative of the natural log divided by the derivative of x minus 1, which is equal to the limit as x goes to infinity of 1 over x over 1, just like before. And now I've got the limit as x goes to infinity of 1 over x. And that limit is 0. 1 over something huge is going to something really small, and so this limit is 0. So there's 2 limits I've computed about a function that I could not do without L'Hopital's rule. The next thing we're going to do is we're going to look at some situations that aren't obviously 0 over 0 or infinity over infinity forms. Let's think about what happens when we have the limit as x goes to 0 from the right-hand side, that's what that plus means, remember, of x times the natural log of x. What happens here? So remember that the natural log of x is defined like this. If I come into 0 from the right-hand side, what that means is the natural log is shooting down to minus infinity. So this part is tending to negative infinity. Where does x go as x goes to 0? Well, it goes to 0. So this part goes to 0. So this product of functions has a piece that's tending to 0 being multiplied by a piece that's tending to infinity. And I don't know which one is going to win. If the 0 is going to 0 faster, then this will be 0. If the infinity is tending to infinity faster, then this limit will be infinity. If they're balanced in some sort of way, it could be any single number between 0 and infinity, or in this case, between minus infinity and 0. This is also an indeterminate form. So this is the product indeterminate form. The way that we fix this one is we use the observation that a product of functions can be rewritten as a quotient of functions. If I have a product fg, I can always rewrite it as f times 1 over g. Because after all, dividing by a fraction is the same as multiplying by its reciprocal. So what that means is, if I have a function of the form 0 times infinity, I can rewrite that function as 0 over 0 or infinity over infinity. Because if f goes to 0, then 1 over f goes to infinity. If f tends to 0, then 1 over f tends to infinity, plus or minus. How can we use it on this problem? The limit as x goes to 0 from the right of x times the natural log of x is equal to the limit as x goes to 0 from the right of the natural log of x over 1 over x. That's just using the rule that I've written in red. Now what can I do with that? Well, if I've turned this into a 0 over 0 or infinity over infinity, I can use L'Hopital's rule on it. So let's see. The top here tends to negative infinity as x goes to 0. And the bottom tends to infinity as x goes to 0. If x goes to 0, 1 over x goes to infinity. So this is an infinity over infinity form, and that means I'm justified in using L'Hopital's rule. So let's apply it. By L'Hopital's rule, that limit then is equal to 1 over x over minus 1 over x squared. The derivative of the top is 1 over x. The derivative of the bottom is minus 1 over x squared by the power rule. And so that means if I do some algebra and I rearrange this, I'm going to get the limit as x goes to 0 from the right of minus x. And that limit is continuous at 0, so I can just plug in the number and get 0. That's generally the approach to these 0 times infinity type exercises. So you can see here that when we have something where we've got a product and that product is indeterminate, that I can use this sort of flipping twice idea to turn it from something I can't use L'Hopital's rule on into something that I can. The final form that I want to talk about is the power form of an indeterminate limit. And in order to work with power forms, we're going to use the e to the log idea that we've been using throughout this chapter. So a limit of functions where one function is raised to the other is going to be indeterminate if I can't figure out by looking at what's happening how this power of functions is going to act. So when is there ambiguity in this? It could be the case that I've got a function that looks like 0 to the 0. And this is indeterminate because this part is trying to make the function into a 0, and a power of 0 is trying to make the function into a 1. So there's a contest here between the base, which is trying to drive everything to 0, and the power, which is trying to drive everything to 1. Another indeterminate form is 1 to the infinity, because the base is trying to drive everything and turn it into a 1, and the infinity is trying to drive everything and turn it into an infinity, or a 0, depending on if you're approaching 1 from the left or the right. The last form is you could have things that look like infinity to the 0. Now you have a base that's trying to explode to infinity and a power that's trying to turn that whole function into a 1. So in this case, this is trying to drive the function to infinity. This is trying to drive the total function into a 1. These are indeterminate because there's a relationship here that I can't just eyeball. Well, we're going to use the e to the log trick to turn power type indeterminate forms into ratio type indeterminate forms. And then we can apply L'Hopital's rule. So as an example, we've already looked at this a little bit. We could look at something like the limit as x goes to 0 from the right of x to the x. So this is an indeterminate form because the base here, the x, is trying to make the function turn into a 0. But the 0 up in the exponent is trying to turn everything into a 1. So this is a 0 to the 0 type indeterminate form. And I can't figure out anything algebraic, and it's not a ratio, so I can't use L'Hopital's rule. So the strategy is going to be to manipulate it until I can use L'Hopital's rule. The trick is the e-log trick. This limit is equal to e to the natural log of x to the x. And of course, remember the reason that we do that is that we want to get this x that's up in the power and drop it out front, so we don't have a function to a function anymore. We have a product of two functions. This is equal to the limit as x goes to 0 of e to the x natural log of x. Now I can take advantage of the fact that e is a continuous function by taking the limit and pushing it up into the exponent. So this is equal to e to the limit as x goes to 0 from the right of x natural log of x. Of course, now this limit right here is a 0 times negative infinity indeterminate form. So there's a product up here, and it's still indeterminate. But notice, I started with a 0 over 0, and I've turned it into a 0 times minus infinity. So I have one last step to do, which is to use the ratio flipping trick. So I can rewrite this as e to the limit as x goes to 0 of the natural log of x over 1 over x. And now I've got an indeterminate form where the top goes to minus infinity and the bottom goes to infinity. And now I can use L'Hopital's rule. So by L'Hopital's rule, this is going to be e to the limit as x goes to 0 from the right of 1 over x over minus 1 over x squared. We already did the algebra on this to show that this is e to the limit as x goes to 0 from the right of negative x, which is e to the 0, which is 1. So this is a typical application of L'Hopital's rule in these cases where you have powers involved. So we have to sort of put together everything that we've done so far in order to do this. We need to know that e and log are inverse functions. We need to know that we've got the log rule where we can take a power and drop it out front. We have to know that when I've got a product of functions that I can turn it into a ratio in order to apply L'Hopital's rule to it. Once I've done that, I need to be able to know that e is continuous, so I can take the limit that's outside the e and push it up here. And then I need to know something about what the values of e are. So this is the culminating idea of chapter 6, where we've put all the pieces together. And what we end up with is a way of computing a lot of limits that we previously didn't have any access to at all. In the next video, we'll run through some examples of these. The exercises in this section are going to look very repetitive in the sense that there's lots and lots of examples of both ratios and non-ratio type functions that you're going to have to practice in order to make this work. So I'll see you for the exercises in just a moment.